And when I had a homework question and I missed it, I mean, here's what okay, I got it wrong. Here's the answer key. Oh, I got it. No, I don't. Put them aside, do the homework question again, and you make the same mistake. Even though 3 seconds ago you're looking at the answer. Try doing it again. You make the same mistake as on your homework, not on the key. You'll catch yourself. Then you look at the key and try again. It usually takes 2 to 3 tries. You do that, you're set. Anyway, work for me. Let's see. I guess I don't have any other stuff right now for you other than, again, homework is due Wednesday. I'll probably just return them on Friday for logistical reasons. Anybody have any other questions? No, we're set? Okay, all right. I guess, it's still early in the semester, and this material is still way boring. Hopefully it's going to get a little bit, more exciting because, again, I know PV equals NRT is high school stuff. And, I'll do everything I can to make it exciting. Get out of here, monkey. You know what I mean. Watch the video. I have to remember that. Okay, so just to review, I always review a little bit. Let's see. Last time we talked, I babbered on and on and on about inexact versus exact partials and how inexact have all kinds of really interesting behaviors. I worked a little numerical problem to show that inexact, when you're integrating these, the path matters. And so you had to do path integrals, which are daunting. That word scares me, but hopefully I showed you one that's not nearly as daunting. And the other fact that I brought up, I think I did this in the next hour, is that there's actually no functional form. If this is the partial of f this is the partial of f and this is its thing, it can't be integrated into a functional form. There's no function that the derivative of which is that. It does not exist. So it's just kind of a neat little fact. So when I have exact differentials, there is also a functional form. I would usually start this class introducing new variables as the change in that variable. And if they're exact, I'll say, and this is what that variable, not change in variable, but the variable is equal to. Now, another thing that I did not bring up in class, but I brought up in the extra hour, and this is actually pretty important, not now, it will be important later, is that if something is exact, then there's this property that the order of differentiation, so if you have a differential, so you put this in here, you would find that for inexact, I'm writing about inexact, that this would not be true. So make sure you know what I'm doing here. This is inexact. This is not true for inexact. And for exact, there would be an equal sign. So make sure you don't get that confused. We're going to use this a lot, in about 2 weeks. So I want you to know that. I just ran out of time last Friday during the main lecture, and I brought it up in the second lecture. Okay, again, I'm still reviewing. And so what this fed into was work. And I kind of blabbered at length about why, minus P exterior dV. Exterior pressure, because that's the thing that's going to be actuating the change. Also, pressure times change in volume. That's terribly important. Has the form of force times distance, force times change in distance. There, I did it again. And force times change in distance is what you heard in mechanics as work. Hopefully that resonates even at a high school level. Force times distance is work. So that's work too. And so there you go. So that works. I thought that was clever. Let's see. Now, the problem though with work is that it's inexact, so there's 2 paths. There's the irreversible, and that has, right now I am defining that as, in class I said, it's like a car piston and there's a sudden pressure increase. And you can imagine that's because gas is being burned. And, okay, that was actually kind of bad that I introduced. So that, I think I did a compression. And for pedagogical reasons, I actually should have done an expansion. So let me do an expansion. And it'll make sense why. And I'm going to answer a homework question as a result. Okay, so when for irreversible, as we're defining it now, is a constant external pressure, E external pressure. I know that constant external pressure, why is that word irreversible? It will be made clear at chapter 4. What it means is that, again, partials are useless. They need to be integrated. or divided by another partial that have a derivative, but by themselves they're pretty much meaningless. Okay, so with a constant external pressure, and again, I'm going to do an expansion this time because it's actually slightly easier to understand than compressions. So I kind of screwed up last time, and again, they'll be made more clear in a second. Let's see, what do I want to do? I'll work down. So we need to integrate it. And because external pressure is constant, it comes out of the integral, and there really is nothing easier. And that's why when I ask irreversible a piston expands, a piston contracts, I'm doing you a favor. Those are way, way easy questions. So there's no hidden subtlety. Lots of times there's hidden subtleties that are hideous, but not this time. This is the only time. All right, so now, as I promised, let me do a graph. And I do try to do as many graphs as possible because some of you understand things graphically, not numerically, but anyway. Okay, now, what I should have done last time is talk about a piston that might, somehow it's compressed. There's a linchpin in it, so it's compressed. And then I pull the linchpin, so what would happen is I have something that was at a high external pressure and that compressed it, but then the linchpin was let go. So now the external pressure has been released, and of course it thus expands. I'll tell you what, let me call that, I know that looks like a number 1, let me call that an I. I never know whether I want to call it 1 or 2 or I or F, right, initial, final. And so then that's right here. Okay. So this external pressure, and there you go. Now, since I'm integrating this, the result is the area of the curve. Again, childishly simple, but there's a subtlety to this. I thought I said there's no subtleties. There is a subtlety to this. It has to do with the other path, the reversible path, which is when the external pressure is matched to the internal pressure. Now recall this. This is terribly important. I never subscript when I'm talking about the system. It's just a convention. It's just other than remembering that, it's relatively easy. So okay. So when that case is, I'm pushing on the piston, and I'm not just letting go and letting the damn thing just go. Instead, I'm just kind of backing off, right? Maybe I'm like scared of it or something, right? So that kind of makes sense. Okay, so the external pressure, it's not quite the same as the internal pressure. It's the same within a differential, which is, of course, arbitrarily small, and you're just slowly letting go of the thing. And this isn't a big deal for this class, but it's like a big deal if you go to grad school. That would actually technically take a very long time to do that if you want to just slowly back off. If you want this to be exactly right, it would technically take forever. Your differential letting go would be a very, very arbitrarily slow process. And the reason that's important is that the integrated work is, see, you can't hide the pressure anymore. You can't hide it outside of the integrand, and that's because it's hiding a factor of volume in it. If the external pressure is equal to the internal pressure, well, the internal pressure is a function of volume. Anyway, and I'm still just reviewing, and this ends up being nRT, and as I mentioned to you in that first Extra Friday, there are just a handful of calc equations you got to remember, and that's one of them. So there you go. And I will have calc expressions on the exam anyway. Okay, now as I mentioned, there's a bit of a subtlety to this. There's a bit of a subtlety to this. I was kind of rushing last time. Let me get these out of the way. Okay, now from knowing how to graph things, here is the irreversible, and again, that's just unbelievably simple. But what happens is, because there's no sudden, in the case of an expansion, there's no sudden drop, the external pressure looks like this. It's just a slow ride down to a, not quite 1 over x looking, but close. Slow ride down from the initial to the final state. And again, I'm still integrating, so the area for the irreversible is the whole shebang. So obviously, the area under the curve in the reversible case is greater than the area under the curve in the reversible. Okay, so that is a big deal. That is a really, really, really big deal, and that's going to affect a ton of things. In fact, I can even use that. That is the way I can actually derive the second law using that, which is kind of funny, because I think laws are things we accept that can't be proven, but I can actually prove the second law using that graph, starting with that graph. I wish I crosshatched the other way now, though. That's the only thing that's annoying me. But anyway, so this guy is horribly important. And I also want to point out, and this is external to all this, so here's a little aside, that the reversible work is more negative than the irreversible. Okay, now, this should throw you for a little bit of a loop, but this is the answer to the theoretical question number 1 on homework 2 from chapter 2. Okay, you accept that the area under the irreversible curve is greater. I mean, I think a 5-year-old could look at that and tell you that. Okay, but I'm telling you it's more negative. And the answer is very simple. Why is that?
There's a negative sign.
The what?
The negative sign.
Right, there's a negative sign. Okay, it's kind of a trick. Yeah, it's unbelievably easy. It's a positive area, but it gets multiplied by a minus sign. And remember, I said that minus sign is going to cause all kinds of problems, that for all our thermoderivations, everything works the same except whenever you see P and B, there's always a minus sign in front of it. That's annoying. But regardless, it makes expansion work negative, right? And remember, I said expansion work is negative. You can remember that several ways as energy is coming out of the system. Its capacity to do future work is diminished. That's negative. Another way to remember that is if I'm compressing it, I'm storing energy inside of it because later it could do work, and that would be positive. So there's lots of ways to remember that. Or you could just graph it and remember the minus sign. Okay, now here's the thing. I did expansion. That's an expansion. I did a compression last time. And I didn't mean to. And I actually meant that to be on the homework, and it still is on the homework, because anyway, I just screwed up. Okay, in an expansion, recall that, no, compression, Jesus, what's wrong with me? Anyway, in a compression, there's a sudden increase in external pressure, and in an irreversible compression, and there's the area. And in a reversible, there would be a slow increase. And there's the area. Okay, so this is your homework question. And I'm going to give you some clues. It is clear that the area under the irreversible is greater. Right? And in no tricks, it's greater. And the irreversible area is greater than the reversible. So it switched from last time. Yet it is true still. This is still true. So I didn't say that this was only true for expansions. This is true no matter what, expansion or compression. This is a compression. So despite the fact that the area under the curve of the reversible is less, it is still a greater negative quantity. And that may seem counterintuitive because the area is less, you have a minus sign, all the reasons why that was true in the expansion is still true in a compression. Okay, now let me give you a hint, and I'm just going to stop there because any of you who attended the next hour, and I did film all that, knows that I will spill answers at the drop of a hat. So I'll get halfway. Here's the hint. Okay, what is a greater negative number? What's a greater negative number? 4 or 3? 3. 3 is a greater negative than 4 because it's closer to, it's closer that way. It's closer to the left. 3 is closer to the left than 4. So therefore 3 is a greater negative number. Think about that and then you'll answer that question. So anyway, so I should stop there. And I'm still reviewing, which is ridiculous, but I tend to do that a lot. So that should be everything you need for work. And heat. Here, let me just say 1 or 2 things about heat. And these are really simple. I'm going to, I'll write it off to the left, and then we have to talk about heat and work. And heat, we're going to get a lot of, heat gets really complicated when we get to chapter 4, but all we need to know right now is what's positive and what's negative. Heat is positive if in. Heat is negative if out. Okay. Now, before you try to memorize that, and let me qualify. Heat in means that I put energy into it, so that's positive. Okay. Now, I could imagine if I was sitting in your shoes that I'm sitting here thinking like, okay, energy into the system, that's like holding a candle underneath the cup of water, like in the picture in the textbook, which I took in the PChem lab, by the way. That would be heat in. And so you're trying to remember, okay, heat in is positive. Okay, there's a way better way to do this. Okay, now, remember that movie or something that little kids are afraid of? Outside in the cold, if you stick your tongue, remember this is like 5th grade, right? If you stick your tongue to a metal pole, you get stuck, right? Okay, you go up to a metal pole and you hold on to it. It's cold, right? Okay, that's how you remember this. Why is it cold?
It's taking energy.
It's taking your heat. Okay, right, it's taking your heat. Is that energy in? Is that energy in? Remember, the metal pipe is the system. Is that energy in?
Yes.
Right, okay. So you can remember that. If you hold on to something and it's cold, that's positive, your energy is going into it. That's why you feel cold. And I think that's even a homework question. Okay, if you touch the metal pipe and heat is going out, is it hot?
Yeah.
It's hot, right. Okay, so anyway, that's just a way to remember this. So it's not just some arbitrary symbology, you got to remember what's up and what's down. That's anyway. So hopefully that'll help you remember. This is actually all I've got. One other thing. Heat is inexact. Now, the beginning of chapter 4, I actually do a thermo proof. It's unfortunately like pretty hideously complicated on how to prove. We're going to do thermo proofs really soon. And you'll see how to prove that heat is inexact. Right now, I'm just telling you it's inexact and path dependent. The thing is about heat, though, I can't graph it. I can't graph it. I can't, with work, this is, like I say, I think a middle school student would understand this. You just have to present it to them. That's the only thing. But heat, I can't graph. There's really not much I can do with heat, other than tell you the two types of, well, they'd be reversible and irreversible. Those are the paths, and they're different. The way that they're different, I show in the book of the case of, the cup, I just mentioned that, a cup with a candle underneath it, like you do in high school, and unfortunately PChem lab, right, when you're doing childish level calorimetry. That would be irreversible. And the reason is a lot of that energy, there's a bifurcation. Some of it goes into the cup and some of it just goes out to the environment. Okay. Now, the other type I showed you was, and this is actually from my research lab, where we do some reactions at really, really high temperature. That's basically what I do. I have a heating mantle and it's all wrapped up in glass wool. And of course the heating mantle has energy going into it. And I can actually put my hand, I do this to freak out my grad students, it scares them to death. This thing can be 400 degrees, I can put my hand on it. That's because it's insulated. So that energy comes from the outside into the system. The system is a 3-neck round bottom. That would be irreversible. And one way to think about that, that's reversible, that's reversible. And the one way to think about that is, all that energy got put in, so probably I can get it all out. I'm not quite sure how. But in this case, think about this. A candle with a cup of hot water. Okay, yeah, I can take that energy that made it to the hot water and I can get it back out. However, I'm not quite sure how, but at least there it is. But the energy that gets dissipated out to the system, you can never recover that. That's like, popping a piece of popcorn, pops popcorn back into a kernel, right? You heat popcorn to turn it into, a pop. You can't put it in the refrigerator and have it go backward. And that's why this would be irreversible. That energy that didn't go into the system because, look at it, it's gone forever. So irreversible. So anyway, that's all I have about heat for now. Unfortunately, when we do start applying equations to heat, that's where things get really complicated, and that's when it comes to entropy. Okay, for now, that's all I have on working heat, but you recall that I actually began chapter 2 talking about internal energy, in which I defined as the energy a molecule has. And as I mentioned, I always begin with the change, because change is all that matters. The change in internal energy is the sum of heat and work. And I've beaten you to death on work. I actually have nothing more to say about work the rest of this class. Excuse me. Work is always the easiest thing. It gets harder. Heat is as hard as it is right now. There you go. They're both inexact. So I won't say that inexact, but get this. This is exact. Internal energy is an exact, and this is nuts, and I don't really fully understand this, but the path dependence to work will cancel out the path dependence of heat, such that the net is path independent. And I don't quite get that. I know that it's true, but there it is. So this is one of those times I just have to tell you that this is how it is, and I really can't explain it further with some folksy explanations, like when my cat threw up on the bed. No, this is just, I don't really get this. It is. It is true. So I can, maybe I do have one explanation, and it involves a cat. Since U itself, here what I want to say, U itself, now remember, if this is exact, I should be able to not talk about the change in U. I'll get more into that later. I can talk about U itself. And since it's exact, there is a U, and it's defined by the Equipartition Theorem. But this is the energy a molecule has. And like I said, I think I mentioned this last lecture, I don't quite remember, I should watch the video. A lot of thermo definitions are really unsatisfying. That's why I studied thermo a lot, because I find these definitions to be very overly simplistic, and I don't really learn anything from it. It's like, all the gasoline I have is the gasoline in my car. Yeah, what? You know, now we're both uncomfortable. I mean, yeah, a molecule has energy, so what? I mean, I think, again, a young child understands that, and yet this is a senior level college class. What the heck does that mean? I'll explain that in a little bit by talking about, well, we'll just figure out what kind of energy the molecule does have. More importantly, because the energy a molecule has is probably as simple as it can get, and it is. This is our starting point for all thermo. All the other types, there's actually other types of energy, like enthalpy and Gibbs energy, which you've heard about, and we have equations for those as well, like delta G is delta H minus T delta S. So you're familiar with those. Behind them, underneath them, derived by, is U. U is hiding in all of those other equations that you actually saw, like delta G. There's actually U in delta G. So what I'm going to do is I'm going to start tacking on other terms, other energy terms to U, and I'm going to build up to delta G. But we have to start with U. Now, you engineers, have you seen U? You have? And chemists, you have? Oh, that's weird. Yeah, you have. But for the most part, I think most chemists have not seen this. Anyway, okay, so the energy a molecule has, so let's talk about the kind of energy a molecule has. And for various reasons, I'm going to first talk about a frozen, we're going to take something simple like argon and N2. Let me just actually even write that down. Let's say we have N2 and or, doesn't matter, argon at 0K. Of course, it'll be a little solid, probably in some scientific apparatus, some giant metal box, and I'm sure it's very complicated. There's all kinds of pumps and electricity being used. But anyway, so I have N2 over argon at 0 degrees K. Okay, now I want to think about what kind of energy it has, but I have to put a little stipulation on this. We have to start thinking about what kind of energy. Okay, now this is thermo class, and I spend a lot of time, especially up to chapter 4, talking about car engines, and then we'll get into chemical reactions. So, as I mentioned to you, a gas expands, a gas contracts is like an overly simplistic chemical change, and then we get into car engines, and then we get into actual chemical reactions. That's the order that we're following. Okay, given that I want to talk about car engines and things like that, and power plants, that puts limitations on the kind of energy the molecule has, because think about this, like, okay, I'm talking about car engines, so let's talk about a car. if you're watching a drag race, they might say something like, the announcer says, oh, and Billy Joe Jean has 500 megajoules of energy in that vehicle. Okay, what do they mean? Now again, it's a drag race. The car is going a gazillion miles an hour, and the announcer is saying, I see this even like on rocket launches. They say, well, there are 5,000 gigajoules of energy being, what do they mean? What do you think?
From the fuel, how much energy?
Okay, so how much energy? Now the fuel gets turned into
Power.
power as manifested by,
Oh, I was going to say that usually the number they're listing is the amount of energy available to do work.
okay, so, I would contend that they're actually just measuring the speed of the object, right? It has a certain amount of mass and then 1/2 mv squared. Right now, maybe some of you who are really nerdy know about that God particle thing. No, that wasn't quite right. No, what was it? There was like some little meteorite was going like 0.9 the speed of light and hit our atmosphere. Do you guys remember reading about that? It was a couple of years ago, but anyway, they said it had so many megajoules of energy. It was like the most energetic particle ever observed. And it was just a piece of dust, but it was going almost the speed of light. Anyway, so when you see car engines, space shuttles, and they say there's so much energy, they're talking about how fast it's going and its mass, right? 1/2 mv squared. Okay, now given that, this is what most people care about. Let's go back to the drag racer. Okay, they're talking about how fast it's going, but is there not energy content from taking that same $100,000, probably about right, $100,000 car and setting fire to it? That'd be kind of awesome, don't you think? You could, right? There's like plastic and foam and stuff inside of it, not necessarily the car fuel. Well, the fuel, okay. Take the whole damn thing and burn it. Do you think they're adding that energy to what they're talking about? Is that the energy they're talking about? No, probably not. And that would be the energy of the electrons, right? That's chemical, that's oxidation. Oxidation, very, very fast oxidation, which the other word for that is burning. That involves rearrangement of the electrons, right? Bonds get lost and new ones are formed with oxygen. So that's all a rearrangement of the outer electrons. Okay, there's another thing you could have done with this $100,000 vehicle. You could have dumped it into a nuclear reactor. Why not? Now that would be really cool. In fact, when I was a postdoc at MIT, this is kind of scary. If you ever go down Massachusetts Avenue in Cambridge, you'll actually see off to the left, when you go north from Boston, there's this big dome building. It's a nuclear reactor, and it's turned on. And so, they're engineers, right? So what they do is, we did this when I was a postdoc. Sometimes you want to study chemical properties as a function of radiation exposure, and I swear to God, this is what they do. You get your chemical, and you put it in a little cup, and you get a really long stick. I'm not kidding. And you shove it into the reactor like that. And then, you burn it, and then you take it out, and you can measure what happened. So there's energy in nuclear reactions. Now, how many of you think when they say that vehicle is traveling with 100 megajoules, do you think they're talking about its nuclear potential?
No.
No, because that's stupid. So I'm not saying that there's not nuclear fuel there by virtue of mass, but that's not the type of energy they're talking about. They're not talking about burning the thing. They're not talking about nuclearizing it. They're talking about how fast it's going. Okay. Now, the point of this long speech is, what kind of energy do I really care about at 0 degrees K? Well, you're not talking about, not nuclear or burning. What really drives a car is, again, what is it not doing? It's not translating. And that's for argon and nitrogen, or for nitrogen rotating. Okay, so as you provide heat and you warm the thing up, then again we're not gonna let it react with oxygen. We're not gonna let it go nuclear. The energy that's being imparted into this, the energy that we could then exploit in a piston type system, is for driving a vehicle, is so it could translate. And for a gas like N2 or argon, when it starts translating, here's the magic piston, right? Sorry, here's the cylinder body, the piston's on top. When those gas molecules start hitting the piston head, then you can start to move, right? That's how the car engine works. So you can translate the space. That's what gases can do with temperature. Again, we're not going to worry, there's energy in that, there's kinetic energy, but we're not going to worry about it reacting or exploding or any of that. Now, in the case of N2, there's rotation. But that's for N2 ETC. Which brings up an interesting point. This is kind of a trivial question, but trivia question. I think it's one of the neatest things I know. I just said that rotation for nitrogen, oxygen, but I didn't say it's argon. You can't rotate argon. Or can you? Does it make sense? If I could shrink myself down and I could grab an argon atom, I'm asking you this, can I roll it? What do you think? The answer is oddly no. You cannot roll an atom. That's not sensible. Now the reason is, and don't write this down, write down you can't rotate an atom. Write that down. Okay. But the reason is that you got yourself a nucleus and you got electrons, right? Well, the electrons are spinning around the nucleus. Now you knew that in high school. But what no one ever told you is how fast. Guess how fast? Like almost speed of light. Almost speed of light. For really heavy atoms like gold, those electrons are moving like with an appreciable fraction of the speed of light. Okay, now think about this. I mean, here's the nucleus, and I'm going to hold on to this argon atom, and I'm going to try to roll it. Now I'm touching the electrons. And by the time I perceive, and let's, by magical means even, let's say that you perceive it rolling once, what have those electrons done? They've circled 10 to the 20 times. So while I perceive it having done one rotation, the thing I'm actually holding on to is actually itself rotated so many times that this is just meaningless, right? So that's the answer. You can't roll an atom, and it's because the electrons that make the body of the thing are spinning so quickly already is that this just doesn't even make sense. It doesn't even make sense to talk about it. So no, you can't rotate an atom. Okay, again, we're trying to get to the internal energy, the energy a molecule has. We're talking about translations. The energy, by the way, rotations are actually kind of bad, by the way. That's kind of bad. It takes energy away from translations. Here's another trivia question. Okay, I've got a cylinder and it's full of argon. Now, I already mentioned that here's the cylinder body, here's the piston head, and the argons are hitting the piston head, and that's what's happening. That's the pressure. Okay, if it was nitrogen, it would be rotating. Would that add or subtract or do nothing to the pressure?
Subtract.
Oddly, yes, it would slightly subtract. Basically what it's doing is rotation would take some of that translational energy. If you gave argon and nitrogen the same amount of heat energy, you would actually have less pressure with N2. That fair amount, maybe like half. You would have less pressure with N2 because some of those rotations took it. And rotations are not perceptible. So I'm the piston head, right? I'm looking down, and getting smacked. Oh God, I didn't mean that. I'm getting smacked in the head by argon atoms. And I'm getting smacked in the head by nitrogen, but the fact that the nitrogen is rotating doesn't make me feel different. I don't get smacked harder. I can't really perceive that part of its motion is not relevant. I don't feel it. And since I'm the piston head, and God, that was awkward. I think about maybe I'll just suddenly transform into a monkey, and then none of that's true. No, I don't feel that. I don't feel rotations as contributing to pressure. So rotation is actually kind of bad, including as well, I didn't talk about this, I intentionally left this off, vibrations, which would even steal more energy from translations. And again, I want to emphasize this. When we're talking about the magic piston, the cylinder body, and the piston head, the molecules translating, which causes them to hit the cylinder head, is what I perceive as pressure. Rotations or vibrations of the molecules would not be perceived in terms of contributing to pressure. Question?
Yeah, how do we have vibrations and translations if we're at 0 Kelvin?
Oh, no. Provided heat, so this is kind of a flow chart.
Oh.
Right, yeah, so I want you to think about, okay, these are like a frozen matrix, and we're heating them up, and what are they doing? And whatever they do, there's energy, right? They can't do things without energy. And although I know I'm kind of maybe overly long-winded, so it gets a little bit lost, my whole point is that energy is flowing to translations, which is good, with some losses due to rotations and vibrations as I beat my head very awkwardly, which is kind of bad actually, because it kind of causes me to lose some of that pressure. And I really want pressure because that's what drives the car. And again, that's my little analogy here that I'm trying my best to get across. So,
Thank you.
okay, so now this is how the energy flows into the system. So the energy that the molecule has is in translations, rotations, and vibrations. For translations, in terms of what we care about, getting the vehicle down the road, the rocket into the air, the translations, the thing that gives pressure to the piston is really what I care about. Okay, so now that I know that, it turns out that internal energy has a definition other than this. It has an equation form, which is via, let me write this down. 1/2, let me talk about a molecule, do kB T per degree of freedom. And this, I don't know if you folks are having trouble seeing this, it's called the Equipartition Theorem. Now, you know I told you I don't like you to memorize a lot of stuff, but this is a big one. You definitely got to know this one. Equipartition theorem is 1/2 kB T per degree of freedom, and that's the energy a molecule has. Okay, now let me break this down a couple of things. Now, for one, I am obsessed with exact and inexact. U is exact. It should, and here's the partial form. It's exact, so it should have an actual equation form, and here it is. 1/2 kBT per degree of freedom. Now remember that kB, in case you forgot, that's the Boltzmann constant, and what that is, it's the gas constant, 8.314 for a single molecule. That's what it is. So I want to put it this way right now because this is for the molecule. But when it comes to a car, right, I really want to think about the per molar. And when I say per molar, I need to put a little m right there. That means per mole. Because I'm not going to drive a vehicle with a single molecule of fuel, right? So that's ridiculous. Anyway, okay, that gets you thinking about the molecules, but we're talking about car engines, so I have to put it that way. Times, sorry, you know, I shouldn't say per degree of freedom. I should say times degree of freedom. Because you take 1/2 kBT or 1/2 RT for a, sorry, I kind of flubbed that. You take that number and then you multiply it by degrees of freedom. Let me use some shorthand, degrees of freedom, and that gives you the internal energy. Okay, now what we have to do is figure out how to put a number to that. Right now, remember, I know I'm being very hand-wavy and I'm using English language. Now I'm using math language, right? So this is some English language that needs to get translated to math language. It needs a number. And thinking about what I had been talking about before, tell you what, let's just do a bunch of examples. And from those examples, we'll have degrees of freedom, and then we have a math language result for internal energy. And we'll do that per mole because we're still talking about car engines. It doesn't quite make sense to talk about single molecules when we're talking about car engines. Okay, gas. Let's calculate the degrees of freedom. And again, I'm going to use a lot of shorthand, so hopefully you follow along and know what I mean. And here's the internal energy. Okay, again, argon is my go-to for a very simple, monatomic, obviously. So that's always my go-to example to be the easiest case. And the translations are three. Three translations. And X, Y, and Z. All right, so that's very simple. X, Y, and Z. So we live in a three-dimensional universe. So that means that the internal energy is 3/2 RT for a mole. Okay, now let me step back and say a little bit more about the equipartition theorem. What it means is, by virtue of having temperature, now hopefully you see why that little weird flow chart I was writing up before, maybe it makes a little bit more sense. When you have temperature, that's energy. And I know how much energy, I multiply it by R. And since I'm doing this per mole, RT has units of joules per mole. Okay, now I've got energy, but what do I do with it? The Equipartition Theorem says anything you can do with 1/2 RT of energy. And everything is equal. If you can do it, then go right ahead, and here's how much I'll give you. So that's how to think of this. Argon, being such a little simple thing, can only translate. There's nothing different about translating in X, Y, and Z. This argon doesn't perceive gravity, right? The X, Y, and Z is a human thing. But it still lives in 3 dimensions, so we have 3/2 RT of internal energy. Okay, let me actually make this a little bit more interesting. Let me go to CO2 as opposed to N2. It just makes it a little bit more interesting. Okay, so that also has 3 translations. Instead of nitrogen, I like to do CO2 because it has a little quirk to it. So anyway. Okay, now rotations. How many ways can it rotate? Huh? I know this is a subtlety, and I don't remember learning this when I was your age. It actually has 3 rotations. Sorry. It should be 3. It should be 3. That's because of the number of dimensions. Same thing. 3 translations, 3 rotations. Okay, but there's a quirk to CO2. That's why I like it. Okay, the rotations are this, and they're this. Okay, what's the last one? What am I missing? This. But does that count? Huh? What do you think?
It'll look the same as well.
Is it? What about argon? What about rotating argon?
Doesn't make sense.
Right, the same deal. Same deal. You can't roll a linear molecule. There's only 2. 2 rotations. Okay, now what about vibrations? I've been ignoring vibrations. What about vibrations? Now who remembers this formula? 3n minus 5 vibrations for linear molecules. Anyone remember that? Did you ever see that before? You should have seen it in freshman. So molecules have, if they're linear, the number of ways they can vibrate is 3n minus 5, where n is the number of atoms. Okay, so that's 3, 9, so that's 4 plus 4 vibrations. Okay, and that gives you 1, 2, 3, 4, 5, 6, 7, 8, 9 halves RT of internal energy. Okay, so there you go. Except that that's wrong. It turns out, for a weird reason, you can't do vibrations. And this is really kind of funky, but the reason is it's a practicality measure. And right now we're doing very practical things because we're practically thinking about how to get that dragster up to 100 megajoules of kinetic energy, right? Okay, vibrations. Now I like to bring this up because this isn't 346. You'll be there soon enough. But there is something you learn in 346 about quantum mechanics, which is that the energy of vibration kind of looks like this. Take a diatomic, right? It vibrates. It vibrates about some central bond distance, and its energy increases in a parabola. And you've seen this before, right? I mean, you probably saw this in freshman, maybe even high school. And quantum mechanics says that there's energy levels to this, and they look like this. What it means is that, and again, 346 we're covering this. I have no choice but to explain it, but I do like introducing 346 stuff. I actually do it all the time in this class. 346 is way harder than this one. When you're vibrating, when an atom vibrates, it's doing this, but it doesn't do this with more energy. That's not true. What I just did there, that doesn't happen. That is not what happens. What happens is it's vibrating, and if I try to add more energy, this is awkward. Nothing happens. Nothing happens. You have to have a certain amount of energy, a certain quanta. That's where the quanta in quantum mechanics comes from. You have to have a certain amount of energy, and when you reach it, when you reach that energy, all of a sudden it does this. There's no in between. It's either this, and if you have enough energy, all of a sudden it does this. And faster, which I can't do because my arms will fall off. it turns out that this is greater than RT. These energy levels are greater than RT. And the reason I like this is that it shows you a little bit more about what internal energy is and what it's useful for. Again, we're being very practical here. We're trying to get the dragster up to speed. Vibrations don't count because even though they're real, I certainly know that things vibrate, you can't put energy into them and then take it out later. In which case, so what? If you can't store energy and take it out, it's the word, by the way, is frozen out. We say it's frozen out. It's completely frozen out of our concept of energy of thermodynamics, so we never consider them further. Okay, so I can tell you folks are getting a little antsy, and I know it's time to go, so I'll basically end there, but I just want to point out that we have a way of calculating U, which I just wrote, anyway, use 1/2 RT, degree of freedom. And now what we're going to do is go back to look at the change in U, the change in work plus the change in heat, and yeah, go from there, using our new definition for internal energy. Anyway, so that's all I've got. Remember, off